Sorry about that. So, new terminology. When we write equations for sequences, we have two types. We have recursive rules, and what that means is if I know the previous term, how do I find the next? If I tell you where I'm at, can you figure out what the next step is? And then the next step. That's what it means if we're looking for a recursive rule. So here's how it's going to be written. To find any value of the sequence, remember n is the sequence number that we're on, and a sub n is what we are calling that term of the sequence. What we'll do in ours is we will look at the one right before it. So if I'm looking for a sub n, what would come right before a sub n? Well, the one right before it, we could call a sub n minus 1. So like if I was looking for the fifth term in the sequence, this would say look at the fourth term because 5 minus 1 would be 4. If I'm looking for the 16th term, I would look at n minus 1 would be 15. So find the term before it. And what was it that our pattern was doing over and over again? Oh, it was adding 2 every time. So we would take our previous term and we would add 2. That's called a recursive rule for this sequence. Okay, we also can write explicit rules for sequences because the recursive rule is all fine and good if you're going in order. But what if I suddenly ask you for the 50th term of this sequence or the 100th term of this sequence? Well, nobody wants to write out 100 terms in a sequence, Mrs. Freeze. So there's a better way to come up with a rule to find that more quickly. We've seen this idea in functions, so you've used it before. But here's what it's going to look like in sequences to find some value of our sequence. So a sub n means some unknown value of our sequence. If we know where to start, which in this case, our first term is a 7. So I'm going to start at a 7. From that 7, I'm going to increase by 2's. So I'm going to put plus 2 here. And I'm going to add 2 repeatedly, over and over and over again. I have to add 2. Well, when we learned about repeated addition when you were a little kid, that was the beginning of multiplication. So this 2 is going to get multiplied a bunch of times. Well, to get to the second term, I had to add 2 just once. To get to the third term, I have to add 2 twice. To get to the fourth term, I have to do that 3 times. So the number of times that I have added 2 is always 1 less than the number of the sequence that we're on. So we're going to write that as n minus 1. Let's try it out. Let's see if this gets us to a 9 for term 2. So if I want to figure out what the second term would be, I'd put a 2 in here for n. 2 minus 1 is 1. Multiply that by 2 is 2. Add 7 to that, you get 9. Okay, it works. So let's go ahead and find the 50th term here. So if I want to put a 50 in for the n, 50 minus 1 would be 49. Multiply that by 2, that would be 98. Add 7 to that, we'd be at 105. So the 50th term in the sequence would be 105, which is a lot easier than writing it out to find the 50th term. So let's label some things on this example so you remember how to do this for problems that you will see. This 7 came from the first term in our sequence, so I'm going to label that a sub 1. The plus 2 is because that is my common difference. Common difference. Because I see in my pattern it's going up by 2, up by 2, up by 2 every time. The n minus 1, the n tells me what number of the sequence I'm on, and the minus 1 is there because I have to add 2 one less time than the number of the term that I'm looking for, so n minus 1. Now, this is kind of a weird looking expression here. I feel like we could do some simplifying with this. Do you see how this 2 is outside of a parentheses? Well, let's go ahead and use the distributive property here. So I could write this as 7 plus 2n minus 2. And then if I combine that 7 and that minus 2 together, I could say 2n plus 5. So this would be another way you could write this explicit rule for our sequence. Both of them are correct. It's fine. You'll see it both ways. Sometimes they'll leave it unsimplified where they have your initial value and then what you're adding or subtracting by multiplied by n minus 1. Sometimes you'll see it simplified a little bit. Now, I want to draw a connection between that and this function table that we have over here on the left. The 2, that would be the slope. If you're thinking about this like y equals mx plus b, the 2 is the slope. And you would see that in the sequence because our y values are going up by 2 every time our x's go up 1. So that is where the slope idea is coming from here. In the sequence, you see it as that's what you're increasing by every time. Now the plus 5, that's kind of weird looking, right? Like I don't see a 5 in the table. However, if you think about this as your y-intercept, the b value, y-intercept happens where your x is 0. Well, I don't have a 0 in my x column over here, but if I did, if I went back and found a 0, could you tell that the a value would be a 5 at that point? 5, 7, 9, 11, 13, 15. So that's where that comes from. That's how it ties in. If you graph this, if it looks like y equals mx plus b, that would be something that would look linear. So this is a linear type relationship that you're seeing. All right, we have a second example here to look at. This sequence or pattern of numbers goes 31, 27, 23, 19. So how is this pattern developing? Well, let's see. From 31 to 27, that's a drop of 4. Down 4. Does that happen again? Well, yep, it does. From 27 to 23, it's going down 4. From 23 to 19, it's going down 4. So we can see what's happening. So I think you'd be able to predict what a sub 5 would be now, because we have a sub 1, a sub 2, a sub 3, a sub 4. So what would come next in that sequence? If you go down 4, you're going to be at 15. If you do that again, you'll be at 11. If you do that again, you'll be at 7. However, if you're asked to find something that's way out there in the sequence, like a sub 50, that's going to get old. So let's come up with some rules that we can use here. So once you see the pattern, the recursive rule is easy to identify because we're going down by 4s. So to find a value in our sequence, a sub n, you take the previous value, which we call a sub n minus 1, it's the one before this one, and we're going down by 4s. So we're minusing 4 over and over and over again. So to develop that into an explicit rule, that's where you tell me the step you want, I'll tell you the answer. You don't have to go and list them all out like you would with the recursive. For the explicit rule, if you're subtracting by 4 over and over and over again, that's going to become the multiplication piece of this problem. So a sub n, we're starting at 31. We're going down by 4s over and over and over again. And the number of times we're going down by 4 is our n minus 1, because you have a decrease by 4 over and over and over again, but one less time than the number you're looking for. So that is our explicit rule for this function. If I want to find a sub 50, I would put a 50 right here. 50 minus 1 is 49. Multiply that by 4, that would be 196. So 31 minus 196. 6. Oh, no. 196. 6 minus 196. 6. 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 6 minus 196. is not right. I didn't mess up. It's fine. It's 196. 31 minus 196 is negative 165. Aren't you glad you didn't have to write out 50 terms of that sequence to find that? So the two examples that we've done so far have both grown by either adding or by subtracting. The word for that is arithmetic sequences. It looks like arithmetic, A-R-I-T-H-M-E-T-I-C, sequence. So arithmetic sequences grow by adding or subtracting. Those are the two examples that we have seen so far. The next two are going to be called geometric sequences, and that means they're going to grow by either multiplying or dividing. Well, our next two examples are going to be examples of geometric sequences. They are ones that grow by either multiplying or dividing. So when you first look at a sequence, your impulse is probably going to be to see if it adds or subtracts. So if I look at example 3 here, I might look at the 5 and 10 and go, oh, it's growing by adding 5. But then that doesn't work here. So I got to go a new way. How else can I get from a 5 to a 10? Well, I could double it. Does doubling it get me from 10 to 20? Yep, it does. It doubles. So this is a sequence where it's doubling over and over again. It's multiplying by 2 every time. Multiplying by 2, multiplying by 2, multiplying by 2. So if you want to find the next term in the sequence, all you have to do is take 40 and double it. It would be 80, and then it would go 160. We've seen lots of exponential growth lately in class and in the world. So this is a sequence that is would graph as an exponential. So let's write a recursive rule for this sequence. Recursive again means based on the previous term. So to find any value, we would look at the previous value, what comes right before it, and in this case we are doubling, we're multiplying by 2. So that is called a common ratio. The ratio between our values here is that it's getting multiplied by 2. So that would be our recursive formula. If I'm multiplying by 2 over and over and over again, that means that 2 could be the base for an exponent. So for the explicit formula, to find a sub n, we want to know what our beginning value is, which in this case is a 5. That would be a sub 1, you could call it. And then we're going to multiply by 2 over and over and over again. The number of times that you're going to multiply by 2 will be 1 less than the term number you're on. To get to the second term, we've multiplied by 2 once. To get to the third term, we've multiplied by 2 twice. So the exponent would be 1 less than whatever n value you're looking for. So that would be our explicit rule. This should look familiar to you from what we've talked about with exponential equations. This is your initial value times here's your base, and then this is what makes it an exponential, that your variable is in your exponent. Let's try another one. I have example 4 here, where our sequence is 324, 108, 36, 12. So you can see it's going down. If you look for something that subtracts, we don't have the same value subtracting every time. Like this is only a difference of 24. That's way more than 24. So we got to look for something else. So you try dividing. I notice right here that 36 to 12, I would have to divide by 3. And that is what works for all of these. 108 divided by 3 is 36. 324 divided by 3 is 108. So this is a sequence that is dividing by 3 over and over and over again. I want you to think of dividing as multiplying by the reciprocal. That's something that you've used for many years now. So we're going to think about this as multiplying by a 1/3 over and over and over again. So for the recursive rule for this, that's where we want to use our previous value. That would be a sub n minus 1. So tell me the previous value, and then take that previous value and multiply by a 1/3. Here you are doubling. The common ratio was 2. It was going up by 2s. Here, our common ratio is 1/3 because it's 1/3 of the size of what comes before it. For the explicit rule, a sub n, I need to tell you where to start. So that would be 324 is my beginning value there. And then I'm going to multiply by a 1/3 n minus 1 times. So that would become my exponent. This would be an exponential decay situation. If your base value is under 1, it makes your curve go downhill. We saw that when we graphed exponentials. All right, so that concludes our video on sequences. So now it is your turn. So on your next page, you will see you have an assignment on Delta Math to practice this skill. Remember, you can call me for help or email me, and we'll set up a Zoom meeting so that we can figure out how to do these. And make sure to remember that Jesus loves you, and so do I. So do your math.